All right, welcome to The Explainer. Today, we're diving straight into the heart of the cosmos. We're going to talk about one of the most basic and honestly just beautiful parts of our universe, stars. Okay, so let's just kick things off with a fact that is, well, it's pretty mind-blowing. And look, this isn't just some random trivia you tell at a party. This is about you. It's about your fundamental connection to everything out there. Which brings us to this first huge idea, this concept that we are all stardust. And it sounds like something from a song or a poem, right? But it's actually a hard scientific fact. I mean, think about it. The iron in your blood, the calcium in your bones, the very oxygen you're breathing right now, all of it was cooked up in the core of a star that died billions of years ago. So what is a star, really? Like, when a scientist talks about one, what are they actually saying? Well, it boils down to this. It's a giant glowing ball of super hot gas or plasma that's being held together by its own incredible gravity. Simple as that. The gravity is so strong, it just crushes everything inward, creating this perfect luminous sphere. And the sheer scale here, it's almost impossible to wrap your head around. 100 billion stars. That's how many stars we think are in our galaxy, the Milky Way, just ours. I mean, if you tried to count that high, one number every second, it would take you over 3,000 years. And remember, our galaxy, it's just one of hundreds of billions of other galaxies out there. The numbers are, they're literally astronomical. Okay, so that's a fair question, right? How in the world do we know any of this stuff? These stars are trillions upon trillions of miles away. It's not like we can just go visit. Well, the secret is that they send us clues. We just had to learn how to read their language, the language of light. Yeah, so every star's light is totally unique, kind of like a cosmic fingerprint. It's not just one solid beam of white light. No, it's actually made up of a whole spectrum of different colors and energies. For our sun, that's the rainbow we can see with our eyes, sure, but it's also a ton of invisible light, like UV and infrared. And here's the really cool part, the key takeaway. All that information in the light points to one single thing. The star's temperature. A star's surface temperature is the master key. It tells you everything. It's what decides the star's color and exactly what kind of light it's putting out the most. So if you look at a really hot, massive star, it's going to be putting out a lot of energy in those shorter, bluer wavelengths. That's why it looks blue. But a cooler star, like our sun, its peak energy is right in the middle, in the range of light our eyes can see. This is why when you look up at the night sky, you see different colored stars. It's not random. It's a giant cosmic thermometer. All right, so we've got 100 billion stars just in our backyard, and they come in all different colors, temperatures, sizes. It's a lot. So how do you even begin to make sense of all that? How do you organize it? Well, what they needed was a map. And that was the big question, right? How do you take this vast, glittering chaos and turn it into something understandable? The solution they came up with was, frankly, an absolute stroke of genius. It's probably one of the most important charts in all of science. And this is it. It's called the Hertzsprung-Russell diagram, but everyone just calls it the HR diagram. The best way to think about it is like a census for stars. You've got temperature running along the bottom, and careful, it's backwards. Hotter is on the left. Then you've got brightness or luminosity going up the side. So you take every star you can find, you measure its temperature and its brightness, and you put a dot on the chart. And when you do that, something incredible happens. The dots aren't just scattered everywhere like a big mess. Not at all. They naturally fall into these really clear groups, like stellar families. You get this huge, obvious band right down the middle. That's called the main sequence. This is where most stars hang out for most of their lives. Then you've got this cluster up here in the top right. Those are the red giants. They're not super hot, but they're enormous, so they're really bright. And then way down here in the bottom left, you have the white dwarfs. They are super hot, but they're tiny, so they're pretty dim. Okay, so here's the most important thing to understand about this diagram. It's not just a snapshot of where stars are, it's a map of their entire life story. Where a star is on this chart tells you who it is, what it's doing, and where it's going. It's a journey. And what determines that journey? It really comes down to just one thing: how much stuff it started with, its mass. Basically, there are two paths a star can take. You have your average stars, like our sun, that kind of live a long, stable life and then quietly fade away. But then you have the heavyweights, the massive stars. They live fast, they burn bright, and they die young in a spectacular explosion. So let's actually follow that journey. We'll trace the life of a star like our sun right here on the HR diagram. All right, so for about 90% of its entire life, a star like our sun is going to be sitting right here, somewhere along this main sequence. This is its long, stable adulthood. It's just hanging out, doing its job, fusing hydrogen into helium in its core. That's the engine that makes it shine. But that fuel doesn't last forever. Eventually, the hydrogen in the core starts to run out. The whole star gets thrown out of balance, and it starts to expand a lot. It swells up, becoming a huge, bloated version of its former self. And as its outer layers expand, they cool down. So on our map, its dot starts to move up and over to the right into the red giant zone. And after it's done being a red giant, the star kind of puffs away its outer atmosphere. All that's left behind is the tiny, super dense, scorching hot core. That's a white dwarf. It's not a star anymore, not really. There's no fusion happening. It's basically a stellar ember, the leftover core of a star that will spend billions and billions of years just cooling down and fading away. And on our map, it's made its final leap, all the way down here to the bottom left. So we've seen the whole life story play out, but does anything go? Are there rules to this game? Are there limits to how big or small something can be and still be called a star? And the answer is a big, fat yes. There are absolutely fundamental limits. It turns out you can't just have a star of any old size. Physics has a pretty strict recipe with a clear minimum and maximum size. And here they are. On the small side, you need about 8% of the mass of our sun. Anything less, and it's a no-go. On the big side, the limit seems to be around 200 times the mass of our sun. Those are the cosmic bookends. Anything smaller or bigger just doesn't work as a stable, fusion-powered star. And it all comes down to physics. If you're too small, you just don't have enough gravity to crush your core and make it hot enough to start nuclear fusion. You just kind of fizzle out and become what we call a brown dwarf, a failed star. And if you're too big, well, you're a victim of your own success. You produce so much energy, so much radiation pushing outwards, that you literally blow yourself apart. You can't hold on to any more mass. And that brings us right back to where we started, doesn't it? The idea that we are literally made of stardust. The elements that make up you, me, and this entire planet were forged inside stars that lived and died long ago. So that leaves us with one last kind of wild thought to chew on. If we are the result of all that cosmic recycling, what will the next generation of stars be made from? And what kind of new things, maybe even new life, will they create?